before we had said if we had had a ring of charge, at the center of that ring, the electric field is 0. But what if we look on the side? Because, we're in a 3-dimensional universe. So side view, there's my ring of charge, and I am some distance z above the ring. And I want to know what about the electric field there. Well, if I look at an oblique view here, some here, distance, then what happens is I have some dq there that's pointing that way. I have dq on the other side, and it has an electric field pointing that way. So dq over there has an electric field pointing that way, dE. Okay. If I have here, it points this way, here, that way. So what happens is wherever I am on the ring, then the x and y coordinates cancel out, but the z coordinates add. So the z component adds. So that means the total electric field is now going to be the integral of all the little dEz's. Okay, so that would give the electric field now for the ring of charge off center from the ring. Okay. Or rather, not in the center, but directly above the center, rather. Okay, so let's think about it. So we've got our ring of charge here. We are some z above. The ring has some radius r. And so I want to find up here, for my little dq's on the edge right there, I want to know, well, what is the charge right there? Okay. Or what is the z component of it? Well, you look at it and say, well, we can look at it and say that if this is some angle theta right there, then we could look at it and say, well, if that's theta, then the z component would be the cosine of theta. So that means the dEz would be equal to, or sorry, not the cosine, but the sine of theta. So it would be equal to the dE times sine theta. Well, what is sine theta? Sine theta in our diagram here is going to be opposite over hypotenuse. Hypotenuse is the distance between the dq and that point z. So that r is Pythagorean theorem going to be the square root of r squared plus z squared. Okay, so that means that my dEz is going to be z over square root of r squared plus z squared times dE. Okay. What is dE? Well, the dE is going to be the k dq over r squared. Okay. Okay. So we look at that and we say, well, that's pretty straightforward then. Okay. So that would be, what is r squared? Well, r squared is going to be equal to big R squared plus z squared. Okay. So that would mean that if we plug all that in, then the dEz, okay, is going to be equal to dEz is going to be equal to the z over square root of r squared plus z squared times k sub b dq over r squared plus z squared. So in other words, that's going to be equal to k sub b z over r squared plus z squared to the 3/2 dq. So ez is going to be the integral dez. So that would be the integral of k sub b z over r squared plus z squared to the 3/2 dq. Now, here's the thing that's interesting, that for our disk here, or not a disk, but for our circle charge, r is constant because it's a circle. As we integrate around here, z stays constant. So that means that all of this is constant. So all that comes out of the integral right there. And the e, which is going to be the integral of the dez's, okay, so that's going to be the ez, and so that's going to end up being k sub b z over z squared plus r squared to the 3/2 integral dq. Well, you don't even have to worry about how you do dq, because you know that dq is lambda, ds, do the integral stuff. You don't even have to worry about that. What's the integral dq? It's q. You don't even have to worry about how you got that. You just know the integral dq is q. So you don't even have to worry about doing the integral, because you know the answer of integral dq is q. I call this integration by avoidance. Okay, so E is going to be kzq over z squared plus r squared to the 3/2. And so that is the result here, okay? And so if that means that you don't even have to worry about how it's distributed around there. Okay, well, now the interesting thing is, if the electric field, and we know the electric field is only in the z direction, so because all the x and y components cancel, so this is k sub b zq divided by z squared plus r squared to the 3/2, and it's only going to be in the z direction. Now, let's take a limit as z gets really big. So what happens? Well, z squared plus r squared is just z squared if z is really big. Z squared to the 3/2 is just z cubed. And so that means that this becomes k sub b zq over z cubed. Well, that is just going to be k sub b q over z squared. So that if you have this disk and you are way up here a really long ways away from it, some z, then the electric field is going to be kq over z squared. Well, wait a minute. If that were a point charge and we're some distance here away from it, guess what the electric field would be? The same. So that means that for this ring of charge, if you're a really long ways away from it, you don't see it as a ring, you just see it as a charge. And so this is kind of a limiting case right there. Okay, now, we did an example in case you happen to be right there, above there. Okay, what happens is that when you get to be about a senior, electrical engineering or physics major, then you learn how to do it if you are in the plane of it, outside of it. Okay, so that's much more complicated mathematics, involves actually a series expansion that you have to find the limit of. Now, if you happen to be in some other direction, some angle theta above the disk of the thing, that is bad. Okay, the only way of solving that is using spherical Bessel functions, and nobody likes to do that. And so that's usually a graduate level thing right there. So we're not doing that. We're also not doing this. we are doing the simple case of right above the center of a ring of charge.